Okay, I think you can see it, but I will zoom it a bit more so that we can talk about this image. This image perfectly um, talks about how the specific RAG works. So RAG is mainly a retrieval augmented generation. It is the entire method is in the name. It retrieves information from a database and it augments them with an LLM. With some other prompts with the user queries and stuff. So it augments them and then it's put down to the LLM for the generation part with the information or the context in this case. Uh, so so it is mainly an LLM. If I like in short talk about why we do RAG, it's mainly because of the LLMs, like large language models have a very uh, to to tackle the disadvantage of large language model. That is, the large language models are very large and becoming larger by each research. So it is very hard for these like 70 billion or 120 billion parameter models to train, and it's very costly and obviously hard. So it's done by big corporations and institutions with access to a lot of GPUs. So it is like, it comes down to the point that it's not environmentally uh, like sustainable or like environmentally damaging to run this much of GPUs to produce, like burn so much energy in the process. So training once is like acceptable because we have actually a large language model. But if you used LLMs in the past, like even in now, if you use ChatGPTs, but ChatGPTs have been like, improving the 4.0 and everything, so they tend to hallucinate, meaning either you ask them or you converse with them on a specific topic and they diverge, or they just straight up give you a wrong answer very confidently. That happens because the LLM does not know how to say no, or I don't know, or or they are not actually updated with the latest information. For example, if the LLM has been trained on the all of the internet uh, on 2021, for example, so it's now 2024. It doesn't know what happened from 2021 till 2024. So if you ask them who is the president now in America, the LLM will not be able to tell you because it is not trained in that specific data. So what's the logical explanation is that year after year you train it with the new data. So again, the cost is adding up. Even the larger the model, and the models are getting larger, so obviously it's like, the costs are increasing in a like exponential manner if we want to talk about that. So to tackle this problem of getting reliable information from an LLM, uh, the retrieval augmented generation, or the RAG process or method, has been introduced. So basically what it does, that we have, for example, in our example of an LLM which has been trained on the data of 2021, so we have this extra data from 2021 to 2024, these like 3 years of data. So we have this data in a format, like in a text format or whatever. So we want to have the data somewhere in a database, and then we want to chunk it. Chunk meaning like it is like very like, it's the literal meaning that we like divided it into pieces, and it might be equal pieces, it might be because there are like different chunking strategies involved. So it is divided into pieces, chunks in this case, and each chunks is converted into an embedding vector. So what is an embedding vector? I think um, to explain you in a very simple manner, embeddings is what machine understands of, like if you give an image in like back in 2016 or 2018 when we used to do like ResNet training or simple deep learning AlexNet trainings, those like when images were given to those networks, they normally converted the image into embeddings, and those embeddings normally explains what the image actually is. So embeddings is normally a vector. It can be a large, like just vector full of numbers. The numbers we don't understand, we don't actually know what those numbers represents, but if we like LLMs understand what the context of the picture or whatever is using the embedding. So embeddings plays a very important role in this machine learning or deep learning framework. So let's talk about okay. 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 Right. Cool. Okay, so we have an embedding model which embeds each of the documents, each of the chunks in our case, and then store it into a vector database, because these databases normally has a lot of vectors. And why we use a vector? Because it's easier for us to find relevant chunks if we do a simple process like simple mathematical calculations called cosine similarity. It is a very, if I just cosine similarity is a very, like we learned it in our bachelor's. It is, here is just very simple calculation between two vectors. What it gives you is how close the two vectors actually are. So I can explain it further than the like Iraq process, I think, but like that's the main key mathematical equation that we actually use to find out which chunks we would require from this vector database. Cool. Okay, so you have the knowledge base. You divide it into chunks, and like we call it documents in LangChain, or I think Llama Index we call it documents, but chunks. Then chunks are, each of the chunks have a specific embedding associated with them, and then those embeddings, as well as the chunks, are stored in a pairwise manner. Like these are the chunks and these are the embeddings, these are the pairs, and these are like stored into the vector database here. So now comes the this is the pre-production part. Like this is what we do before the RAG pipeline or the LLM is being used for like general purpose. So after each of the documents have been like turned into an embedding and stored into the vector database, we come into the production part where we actually like use the RAG pipeline. So first comes the retriever part. The retriever part is simple. We retrieve the relevant documents from the vector databases. How? Firstly, we ask a question. For example, who's the president in the United States in 2024? This might be a query. So we put the query and then we turn the query into an embedding. The same embedding model is used in this case. So what it will do is that this embedding model produces a vector, and this vector is like we find the closest vector to the query vector using the cosine similarity. And when we find we'll find few of them which are fairly close, we either take the closest one or we take the three most closest one. It depends. But if we take just one, the closest vector, and then we take the associated documents with that, we take the vector, the closest vector, and we obviously have the associated like corresponding documents with that vector. So we take the documents and we use the vector to match the closest documents, because otherwise it's not possible for the sentence-wise matching is not exactly possible. That's why we converted it into vector, so that we have something to match with. So when we have the like most relevant documents related to that, we take the document out, or we take the text out, or in this case here it says the top k similar documents. They are like, top k meaning k can be a number, it can be 2, 3, 4, 10. So we take the most similar documents or similar vector, and then we take the associated similar documents, and then we produce the context what we want to send to the LLM. So this part is quite simple. So we take the query, the user query in this guy, yeah, excuse me. So we take the user query and the context. That the context contains all of the documents, like which we retrieved. It can be 1 to 10, like the k number of documents, the contents of the documents in a appended manner. And with the query and the context, we make one prompt, like on top of the prompt. It can be the user query, below it can be that context, and these makes the entire LLM prompt, and that is the thing we give to the LLM. So now the LLM does not actually have to rely on its own information, because in the prompt we tell that this is the question, this is asked by the user, and this is the context that you're going to work with or find the answer from. So give us the answer from the context. LLMs, especially the instruct models, are very good at following instructions, because those are trained like to follow instructions of the users. So when we specify the LLM prompt to actually like get the answer from the context, so it does that fairly accurately. So it doesn't have to rely on his false information or the information that it actually has from 2001. It normally finds the answer from the context, and then gives us the answer back. So it is a very fairly accurate method in terms of getting the accurate answers. So this is the entire RAG process in a very simplified manner. Cool.